Hi, I'm Nick, and I'm part of Duke Robotics Club. In this video, we will take you through the tasks we plan to attempt and our approach for each task. To understand our approach to the tasks, we first describe a few of the important components and sensors. Our robot is shaped like a cylinder, and it has 6 degrees of freedom: X, Y, Z, which are the translational degrees of freedom, and roll, pitch, and yaw, which are the rotational degrees of freedom. Roll is rotation about the x-axis, pitch is rotation about the y-axis, and yaw is rotation about the z-axis. Our robot has 2 cameras facing forward, what we would consider to be the positive x direction, and 1 camera facing downward, what we would consider to be the negative z direction. We also have 2 sets of hydrophones on the robot to pick up acoustic pinger signals, one for coarse approximations and one for narrowing down the location of the signal. We use an IMU, inertial measurement unit, and DVL, Doppler velocity logger, to know the current position and velocity of our robot, both in the global pool frame and the local robot frame. The robot has claw and marker dropper actuators for the octagon and bin tasks respectively. We now review a few fundamental software components of our robot. We have deep learning-based 2-dimensional computer vision operating for all 3 cameras. This allows us to draw bounding boxes around objects in the vicinity. Also, since we have 2 cameras facing forward at slightly different positions, we can compute a disparity map between the images captured by the cameras to obtain a depth measurement for objects in front of us. This is called stereo vision. Using the frame width and height of the camera, we can convert bounding box coordinates and the depth measurement into position coordinates in the robot's local frame. In this way, we can know where all objects are located in the robot's local frame using computer vision. Our robot uses cascading PID control to move to desired positions and achieve desired velocities. Cascading PID is a nested feedback loop. The inner loop, which runs at a very high frequency, governs velocity, and the outer loop, which runs at a lower frequency, governs position. Overall, the PID system compares our current position or velocity to the desired position or velocity and controls the thrusters to minimize this difference. And the nested part helps us because the inner loop, which runs at a very fast frequency, is able to correct for local disturbances, while the outer loop, which is the position loop, makes sure that we are generally going in the correct direction. We have an overall task planning algorithm that uses all these components to move the robot through the course. The first task is the gate task, which is required. We will elect to do a coin flip to decide our robot's initial heading. Since our robot will not be facing the dock, we will rotate the robot clockwise until we capture both the middle tick and the right side of our gate with computer vision. We will then use our frontward stereo vision to compute the distance to the middle tick and right side of our gate. Using some vector algebra, we obtain a normal vector to the gate, and our PID controls algorithm will allow us to travel along this normal vector through the right side of the gate while maintaining heading. Once we travel to the right side of the gate, this will officially be a bootlegger run. Using PID velocity control, we will be able to do this with style. We will do 1 barrel roll and 1 rotation about the z-axis as we go through the gate. After we pass through the gate, our computer vision on the downward-facing camera should capture the path marker. Our robot will navigate to the buoy task using the path marker as a guide. We will do this by finding the x and y coordinates of the middle of the path marker with computer vision, and we will use those as PID set points while keeping our z position fixed. So we just follow the path marker. Once we reach the buoys, we will use computer vision to draw a bounding box around the left and right sides of the bootlegger buoy. And we will then use stereo vision to find the distance to both sides. And we will use vector algebra to calculate a normal vector to this buoy. Again, our PID controls algorithm will allow us to travel along this normal vector to bump the buoy, completing the buoy task. Since we have not yet seen the course in person, we are unsure whether we will be able to see the next path marker in our downward-facing camera after we complete the buoy task. So what we're planning to do is we're planning to search for the path marker in all of the cameras, find out where it is, then convert it to a position in the robot's local frame, and then use PID in order to bring our robot right above it. Now the path marker should be easily visible in the downward-facing camera of the robot. And once we do this, then we can just simply follow the path marker to the bin task in exactly the way we did before when we follow the path marker to the buoy task. At the bin task, we first use computer vision to locate the bin containing the images corresponding to the bootlegger. We navigate our way there the same way we did for the buoys, except we don't actually want to hit the bin, so we're going to stop short and then reset our orientation so that the bottom of the robot is parallel to the open part of the bin. Of course, this doesn't guarantee that the marker dropper actuator is actually right above the open part of the bin. And this is something we're going to have to address once we're on site. We're going to need to understand what the image captured by the downward facing camera should look like when the marker dropper is in fact positioned correctly. But assuming we can get the robot positioned correctly so that the marker dropper is over the open part of the bin, then we just trigger our marker dropper actuator and we drop our markers. Although we have a functional claw, we're unsure of the claw's reliability, so we are not yet sure whether we are going to try to lift the cover off the bins. After the bins task, we will elect to turn on the pinger at the center of the octagon task. We are planning to skip the torpedo task. Our acoustic system will guide us to the pinger. First, one set of hydrophones will find the octant where the pinger is, and the second set will narrow down the exact location within that octant. Once our PID system takes us to the location of the pinger, we will surface inside the octagon and finish the run. We are unsure whether we will attempt to pick up any bottles and place them on the bootlegger table. This is something we will decide once we see the layout in person and we are able to test our claws on the competition bottles. Thank you very much for listening.